So let's take a look here at a major topic of study here in calculus, and that is what's known as rectilinear motion. Depending on what text you look at, you might also see this called kinematics. You'll study this in physics if you're, whether you're in it this year or upcoming years, you'll be looking at this kind of a concept. But the whole idea behind what we're dealing with here is the idea of motion along a straight line. Okay, and you're like, well, what, we're just running back and forth? Well, kind of. All right. Basically, we could have something that's moving in 2 dimensions or even 3 dimensions, but we're only looking at it one-dimensionally. Okay, so there might be something flying through the air, but we're only looking at its vertical height off the ground. We don't care how far it went horizontally. We're just looking at its movement up and down. Or there might be something that's, oscillating back and forth. We could see that with some kind of a sine function moving back and forth, okay? But basically what we have is we have 3 different functions here that all use the independent variable of time, okay? So we're dealing with movement here. Now, our basic function is the displacement function, okay? Often we use x of t. You may also see people use s of t, okay? But this is a vector distance from the starting point, or displacement. How far are we away from where we started? Now, depending on how the motion has gone, that is not necessarily the same thing as how far we have traveled. Okay? Let me illustrate. Let's say here is 0, and I'm on this number line here. And let's say that initially our object starts moving this way, and then it changes direction, and it comes back this way, and then it changes direction again, and then maybe again, and then it comes back here, okay? Now, how far away from my starting point am I? 0. So guess what? My displacement at this moment is 0. Okay? Is that how far I traveled? No, obviously. Okay? It's kind of like NASCAR. All right? We drive 500 miles, but we go nowhere. Okay? We end up right back where we started. We actually haven't gone anywhere. Okay? After 3 or 4 hours of driving or whatever it is. Okay? So, and that actually has some implications in physics, because when we study work is force times displacement. Okay? So you could say NASCAR drivers never work because they never end up going anywhere. So from a physics standpoint, they do no work. If you don't end up any further away from where you started, then you've done no work. So there's some implications there for physics, but also just looking at, again, where we're at in relation to this. Now, it is possible to use a displacement function to figure out distance. Okay, and we'll actually deal with that later, but that's our initial function that we're working with here. Okay? Then we have velocity. Okay? Velocity, or v of t, is our instantaneous rate of change. We've been talking about rate of change a little bit in our last lesson. Okay? We know that the derivative is the rate of change. Now, this is a vector quantity. It's velocity. It's not speed, necessarily. Okay? It's telling us how fast our object is moving, and it's telling us in what direction. What tells us the direction that we're going?
Sign.
The sign of it. Is it positive or negative? Okay, so in the example up above here, okay, from the start over to here, this has a positive velocity. From there all the way over to here, this segment there has a negative velocity, and so forth, okay? The velocity tells us which direction we are traveling, okay? So positive velocity, change direction, negative velocity, then positive velocity, negative velocity, positive velocity, and negative velocity, okay? Let me change this other positive one to green, okay? So we have here the sign of our velocity is going to indicate a direction, and its magnitude is going to indicate the speed, okay? The speed. And that actually is something that we can see here. Our velocity, or for our velocity, the absolute value of velocity is going to give us the speed. Okay? So that's a good distinction that you need to make sure that you make. Okay.
The magnitude was how far you are from 0, or no?
Yeah, in velocity, yes. Okay. Now, notice here we find velocity by taking the rate of change in our displacement over time. In other words, the derivative. Okay, dx dt, or x prime of t. All right, so then we have a third function. The third function is the rate of change of the velocity, and that's the definition of acceleration. Okay, so you see here, acceleration is the instantaneous rate of change of the velocity. That is also a vector. Okay. The sign indicates which way we are trying to move. Okay, and this is something that can often be challenging for people to understand, is the fact that our acceleration can be the opposite of the direction we happen to be traveling. And we'll talk a lot more about this, okay? But I like to think of acceleration as the direction we're trying to go. Even if we still happen to be going the other way, we're trying to go the other way. Okay? Now, like we said, it's the instantaneous rate of change of the velocity. So it's the first derivative of the velocity function. It is the second derivative of the displacement function. Now, we haven't really mentioned second derivative. What do you think that is? Yeah, it's taking the derivative of the first derivative. Okay? So the first derivative we get the velocity. We take the derivative again, and we get the acceleration. Okay? So, by the way, notice the notation here for second derivative. You can use double prime here. Or if you have the dx dt, it's the second derivative of x with respect to t. And you have the little squared there. Okay? The reason why it's that way is because we are taking the derivative with respect to t of the derivative of x with respect to t. Okay, so that's how we end up with d squared x over dt squared. Okay, that's where that notation comes from. All right.
Is there a specific notation you'd want us to write, like, on if we're answering one of those questions? Does it matter if you write, like, the x prime of t or the d squared x with respect to?
It really doesn't matter how you write it, how you choose to write it. It's more in the case of if you see it, you should recognize it, regardless of which way it's written.
So you should write ahead the question as it right?
Yeah, typically we'll try to use the same notation that the problem is using, but I really don't care. As long as you're using valid notation, it's totally fine. Alright, so, and here at the bottom you also see speed is the magnitude of the velocity. So, let's deal with that concept that I said was a little bit challenging to understand, and that is the fact that acceleration is not necessarily in the direction that we're trying to go. Okay? How many of you guys have a dog or a cat? Anyone? A couple of you? Okay. Not a whole lot of pets here. You ever see a dog or a cat run on like a tile floor and they try to change direction? Yeah. And you see them like scrambling and they're just sliding across the floor? Yeah. Okay? You know what's happening at that moment when you see them sliding but you see their feet trying to go the other direction? That's what's happening when our velocity is going this direction but our acceleration is going the opposite direction. Okay? And what happens is eventually they do stop. So in that time, while they're sliding but they're trying to go the other direction, what's happening to their speed? It's decreasing, it's slowing down until finally their velocity hits 0 and they're actually able to gain some traction and start going the direction that they want. Okay? That's what happens. That's kind of the interplay between acceleration and velocity. Okay? Acceleration, that's why I say acceleration is kind of like what you're trying to do, and velocity is what is actually happening in relation to your movement. Okay? So, for example, in this case, if my acceleration is going in the negative direction and my velocity is going in the positive direction, that is going to slow me down. Okay? Or it could be the other way around. I could be trying to accelerate in the positive direction, but my velocity is in the negative direction. That's also going to slow me down, okay? Anytime our head is trying to do the opposite of what our body is doing, it's going to slow us down, all right? And that's kind of the idea here. However, if they're agreeing with each other, we're going to go faster if both the velocity and the acceleration are positive, or if both the velocity and the acceleration are negative. Okay? Now, how large our acceleration is, from a magnitude standpoint, will simply be a matter of how quickly we're able to change direction. Okay? So. Alright, so let's work our way through an application. A lot of this has been worked out already, but I want to actually show all the work here and make sure that we understand what's going on. Okay? There's also a table here. I'm going to show you an alternative way of representing this information that you may prefer. But yeah, let's go ahead and look at this. We're given the displacement function. An object travels in the x direction with its displacement from the y-axis in units given by 3t cubed minus 30t squared plus 64t plus 57. And we're going from 0 to 10 seconds. This is, by the way, another thing you're going to see a lot more. You're going to see a domain for your time. Okay? Please make sure you follow that domain. If you're asked to sketch a displacement function or something, only do it for the domain that you're given. Okay? In fact, if you're asked to sketch any function, only do it for the domain that you're given. Okay? So, there's our displacement. And you can see here we have velocity and acceleration already given. Okay? That velocity and acceleration are the first derivative and the second derivative of our displacement. Okay? So x prime of t, we have 3 times 3 is 9t squared, minus 2 times 30 is 60, t to the first, plus 64 plus 0. Okay, so that's where we got our velocity function from. Okay, and then if I take the second derivative, that's going to be our acceleration. Yeah, 9 times 2 is 18, t to the first, minus 60 plus 0. There's the acceleration function. Now, let's examine each of these for a second, because for all of these functions, one of the very important things that we're going to look at are the zeros. Okay? Now, for this one, I'm not going to focus so much on the zeros of our displacement, but let's look at the zeros of our velocity and acceleration. Okay? So, when v of t equals 0, what's happening? It stops for a moment. Okay? It stops for a moment. So, if I set that 9t squared minus 60t plus 64 equal to 0, you guys all know how to solve a quadratic, but we end up getting t equals 1.33 and 5.33. Okay? You can see that down here. Okay? So, let's map this out for a second. Okay? Let's map this out. If I have my number line here, and here is 0, first of all, when I'm at 0, what is my velocity? 64. Where am I at time 0?
At 0.
What's my displacement? 57. You don't have to start at 0. Okay? So, I'm over here at 57, and I start with a velocity of 64. That means I'm traveling which direction? I'm traveling to the right. Okay? Now I'm traveling to the right. Here's t equals 0 until I get to t equals 1.33. Because at this point I stop. Alright? Now, you guys know that because it's a parabola, it was positive. Once it hits 0, what happens? It goes negative. Okay? So now, I know that I'm going to be traveling to the left until 5.33. Okay? Now, if t is 5.33, I want to see how far I'm going to have to go. Okay.
Because you plugged in 5.33, it comes out negative? Or no?
Well, if you look at, actually we know because of the graph of this, if we sketched a graph of our velocity, okay, from 0 up until 1.33, it would look like this. And then between 1.33 and 5.33, it would be down below the x-axis, and then it would come back up above. Okay? So there's the 1.33. Here's the 5.33. By the way, at that 1.33, we're over at 96.1. At 5.33, we are at almost 0. Okay? So this goes all the way over here. This is actually a 0.111. Okay? But that's where time equals 5.33. And then after that, it's going in the positive direction until we hit 10 seconds, right? And at 10 seconds, it's at 697. So it goes way over here. 697 when time equals 10. All right? So right off the bat here, we can kind of see the motion that's happening here. Okay? But that's just part of it. Notice here our velocity helps us see when we're moving to the right and when we're moving to the left. Okay? Now, this is where you have a table down here, and if you look at this first row of the the first two rows of the table, at the moment we're going to ignore this middle row, or this middle column here. Notice when we start at 0, our velocity is a positive. It was 64. It hit 0 at 1.33. It hit 0 at 5.33. And then over at 10, it was positive again. Okay? But notice how between 1.33 and 5.33, it's negative. Now, guys, you can figure this out a number of different ways. We used the graph because we know what the parabola looks like in order to figure out what these signs are. But what this table is it's referred to as a sign diagram. Okay, a sign diagram. And basically what you do is you put your zeros on there and then you plug in any number, in this case, any number between 1.33 and 5.33. If you plug in 2 in our velocity, you're going to get a negative number. Okay? If we plugged in 4 or, 3, all of those will give us a negative number. So I know that it's negative between the 1.33 and the 5.33. So what does that tell me? Well, that tells me the answers to 1 and 2 here. Okay? 1 and 2. When is the object moving to the right? Well, when would that be? When what?
When it's not between 1.33 and 5.33.
Okay, so when the velocity is positive. Okay? So we would say here it's moving to the right from 0 up to 1.33. We can use a bracket on 0, but you should use a parenthesis at 1.33, because at 1.33, what's our velocity? 0. It's no longer moving. Okay? Or from 5.33 up to 10. Whoop. Got my 10.
So when you plug in 1.33, it comes out to 96.1.
No, the velocity is 0. Our displacement, these are all x's down here.
That U means or.
That U means or, yeah, union. Okay? So when are we moving to the left? We're moving to the left between the 1.33 and the 5.33. Okay? So So this is how we can use this table here to help us see some things. You put the zeros down, and then you test numbers between the zeros, and that'll tell you which direction it's moving in that interval, okay? Does that make sense? Okay. So now we have the acceleration, okay? The acceleration. Again, the acceleration tells us which direction we're trying to go. All right, so the acceleration is 18 minus 60. So the acceleration at time t equal to 0 is not going to tell us when we stop. It's going to tell us what?
When you're moving at the same speed.
What?
When you're moving at the same speed, like continuously.
Okay. It's a moment in time where you are not trying to accelerate or decelerate, we could say. All right, so it's that moment of change. Okay, it could be a hesitation where we're not trying to accelerate at all. You're right. Or it can be, and what happens more often in these, it's that moment when we're changing our mind about our direction. You can think of it that way. It's a change in the direction we're trying to go. Okay, so if you look at our picture down here, we actually hit a velocity of 0 there. We hit a velocity of 0 there. Okay? Looking at our acceleration, it equals 0. 18t minus 60 equals 0. When t is 60 over 18, which comes out to what? 30 over 9, 3 1/3. Okay? So 3 1/3. Now, you'll notice down here, we have a 0 in the table for our acceleration at 3 1/3. Now, that is somewhere around here. Okay? That's when we changed our mind. So from the beginning, if you plug in a 0, our acceleration was negative, right? Negative 60. So we are traveling to the right, but we're trying to travel to the left. So what's happening here between 0 and 1.33?
Slow down. We stop trying.
It's slowing down. It's slowing down. We are still moving to the right, but notice here our velocity, or I'm sorry, our acceleration is trying to go that way. Okay? So in that range right there, we're actually slowing down. And again, that's because, notice these are opposed to each other. We are slowing down. Yes?
On a test, would you want us to draw out this whole little diagram here, or can we just identify what's speeding and slowing and moving?
If you use the table, or I'll actually show you another way of representing this same thing. It's actually a way I typically will do it. I think it's sometimes a little bit easier to see things with. One or the other you'll want to do, just to help you see everything. Okay? So we're slowing there. So then we have this region in between here, okay? What's happening right there? We stopped at 1.33, and now we're moving to the left. Which direction are we trying to go? To the left. So that means we're going to be speeding up. Okay? So right here in this range, we're going to be speeding up. Okay? Between 1.33 and 3.33. Okay? But all this time we've been trying to go to the left. Now all of a sudden our acceleration hits 0. Okay? And now all of a sudden we decide we want to go to the right. So yeah, notice here we're still going to the left, but we're now trying to go to the right. And that means we're going to slow down. Okay? And then finally, our velocity hits 0 at 5.33. We start moving to the right again. Our acceleration is to the right. So since those are agreeing with each other, that's going to cause us to speed up. Okay? All right, so when is it speeding up? That's going to be on the interval from 1.33 to 3.33, and also from 5.33 up to 10, and we can put a bracket on 10 since it can equal 10. But then when is it slowing down? It's slowing down from 0 up to 1.33, or also between 3.33 and 5.33. Okay? So that's the idea with that. Let me take all this data and show you one other way of representing it that you may prefer. Okay? Rather than a table, I typically will prefer to just use a number line like this. And what I'll do is I'll put my zeros on it. So here's a 1.33. And here's 5.33. This whole thing is starting at 0 and ending at 10. Okay? But notice our velocity between 0 and 1.33 is positive. It's negative between them, and it's positive here. Okay? And then what I'll do is I'll put, right below it, I'll put my acceleration. And it equals 0 at 3.33. And it's negative here and positive all over here. Okay? And then what that enables me to do is I can identify the different ranges. Okay, here's where I have positive and negative, so that's going to be slowing down. Here's where I have negative and positive. I'm going to be slowing down. Here's where I have negative, negative, so I'm speeding up. And here's where I have positive, positive, so I'm going to be speeding up. Okay? just an alternative to the table. Some people find the table confusing. Some people find this confusing. Whichever one works for you, just go for it, okay? So here on the second page, you can kind of see the graphs, all right? And if we look closely at the velocity, I sketched this already, but here our velocity is positive, and here our velocity is positive. Here was that 1.33 and the 5.33. So if we're thinking of it in terms of our motion, we were moving to the right up to here, we stopped, then we were moving to the left, and then we stopped at 5.33, and then we were moving to the right again. Okay? For our acceleration, here's that 3.33. We were trying to go to the left until we hit 3.33, and now we're trying to go to the right. Okay? This is another way, if you're on your graphing calculator and you graph both of these together, okay, think of it like this. We've got this graph, and you can see here as well where we're speeding up and slowing down. Okay? Right here, one's positive, one's negative, we're slowing down. In this interval from here to here, we're both negative, so you're speeding up. From there to here, one's positive and one's negative, so you're slowing down. And then after you get past there, they're both positive, so you're speeding up. Okay? So guys, you can use a sign diagram, you can use a table, you can use the graphs like this, but there are a lot of different ways that you'll be able to find where we're speeding up, where we're slowing down, which direction we're going, and that sort of thing. Okay? All right.